Aquellos que tengan vehículo y puedan llevar gente, por favor.
All right. Welcome back, everybody. It looked like we lost all our online people because I think the feed went offline. Oh, one is watching again. They're coming back. Okay. Maybe I take the first moments to show you a little bit where you can go to get LAS tools, the latest versions, get help, join the user forum, and so on. So the main site of LAS tools is now on rapidlasso.com. And first things first, if you want to download the latest version of LAS tools, you do have the latest version of LAS tools right now. Actually, you have a version that's not even out yet. You have the most recent version. You just click here on download, and the download will start, or you click on the LAS tools toolbar here, and you get the download here. I should update that page. It's now up to 26 megabytes, the download of LAS tools, without the data sets. The reason your version today was 220 megabytes is because it contained all these data sets and also the PDFs and the PowerPoint presentation that I gave earlier. A very useful place to go. By the way, all the READMEs are also available here. Every tool's README is also online. You know, if you just click here on these READMEs. A very useful thing is listed under support. So if you just click on support, it gets you to the Google Groups user forum. That is a quite active, and let's see, about group of users. It's now up to 2,500 members. And if you have a problem with LAS tools, like a very common problem that I often get emailed about is last ground error. You know, some error happens when you process with last ground. You can just type it in the search bar, and you get every question that's ever been asked, together with all the answers that have always been provided, about last ground error. Similarly, if you want to use a tool we're not going to use today, because this is not really a forestry-centered workshop, but if you want to know something about what last canopy is really doing and how to use it, you just type in last canopy, and you will get, you know, either sorted by relevance, according to whatever Google's magic algorithm is, or by date, all the topics that have been containing the word last canopy in the past. I think I started that in April 2011, so in the past 4 years. And, or even something, you know, some people, they use last tools and then they say, how do I cite last tools? Well, you just go in, cite last tools. And, you know, you get my answers to how I think is a good way to cite last tools if you want to do so. So this forum is really useful. There are also discussions in there which, like recently we had a discussion about what is the difference between an ellipsoid and a datum. Like I'm a computer scientist. I don't come from the field of geodesy or geomatics, so there's a lot of things that I still need to learn. And I learned a great bit from that little discussion. So you can also become a member, and then you get the emails automatically sent to you, about 5 emails a day. So then you should also make an automated rule to put it into a specific folder. Well, you have to ask Google that. The problem with trusting Google is, of course, it's a private corporation. One day they may decide they no longer support Google groups and everything will go away. I hope the outcry would be loud enough in this case that they will not do this. Especially their search engines are indexing Google groups. So it should all be in Google groups as long as Google is hosting it. I'm not sure about the future of Google. But there has been another forum run by the USGS, the LiDAR Bulletin Board, CLIC. Due to the paranoia, you know, about security and blah, blah, blah in the US, one day there was just this blanket thing that they had to shut down all these kind of online forums. And the collective memory of the LiDAR community of the last 7 years, including a lot of interesting discussions about the development of the LAS format. I had invested serious time into that forum in answering questions and so on. They were all deleted. And you know, they promised to make it available in some other form someday. They never have. You can still find it in the Google, in some web time preserved engine, but not everything. It's incomplete. So that was, you know, the USGS of all places deletes, you know, the LiDAR forum. So if you know, if even that happens, so with a private corporation, I guess, you know, we're up to well, I hope they'll never close that down. Or if they do close it down, they give us enough advance warning or a mechanism to copy it in a clever way into some other forum. And yeah. What else do we have? The tutorials that are as PDF files in your distribution are also all available online. There's a whole bunch of videos now. I hope this will also be one of those videos. I'm not sure it's going to be recorded and put online someday. Then it also will be eventually listed under videos. A LinkedIn group. I'm not sure that it's going to work. So if you want to join Last Tools on LinkedIn, there's also some interesting discussion going on. You know, I post things, some other people post things once in a while. And finally, and that's the most fun part of Last Tools, that's the Facebook page. So if you go to facebook.com/lasttools, you find a lot of stories. Like, you know, I posted here, for example, that we are live today on YouTube. And here, that's the story about this ellipsoid versus datum. You know, how an ellipsoid how every datum has an ellipsoid, but one ellipsoid may be part of multiple datums. That's explained here very nicely. And new features are announced, like multiple file delete is now available. And, to delete multiple files from the GUI. I post cool videos I find, pictures of me working on defeating ESRI in their attempt to lock in LiDAR with a new format. Funny pictures. These tend to be quite popular. By the way, you see, this is a mug. I don't have it today. I mean, this mug is actually not the real Last Tools mug. Yeah, but thanks for putting it there. It almost looks like it was mine, but it's not. We left it at the winery. Unfortunately, I saw that first, but then it said, oh, we left it there at the wine tasting, so now we really have to go back for another wine tasting. Yeah, I post pictures about this big tour I did in the Philippines, and all the problems we encountered. I tried to document them mainly for the people that are part of the program, including scripts and good advice, at least the best advice I can come up with for quality checking, quick quality checks for large national LiDAR projects. And yeah, here we announced this workshop. And some pictures from and so on. So there's a lot of fun stuff. So if you want to follow it, just search for Last Tools on Facebook. Okay. It's time to move away from Europe. So we did France, and we did Poland, and we did Australia, FUSA. There was Flinders University of South Australia. Now it's time for some really local LiDAR data, and we are very fortunate that the campus has been scanned, part of a ENCALM scan. And you have this data now. It's in the CICESA folder. So I would say, let me see, where's my... Oh, I lost my Explorer. There we go. So I would let's start with a tool we haven't used yet, and that is a tool that creates these overlap checks and does the flight line alignment checks. It's called LAS overlap. Now be a bit careful, because there's a tool that is very similarly named. It's called LAS overridge. That does something completely different, and we won't use that tool today, because that's a bit more of an advanced tool. So LAS overlap. And it should say in the top corner, quality check LiDAR flight lines for overlaps and alignments. And if we now browse, very convenient, the CICESA folder is right here. And you go in there and you see, whoa, so many folders. Well, I created all these folders for you because we will use them all today. They're all empty, except one. And that's the strips raw folder. So if you double-click on the strips raw folder, you see 5 strips. These are the strips I obtained from Alejandro. I haven't really done the entire pipeline. So it's a bit hit and miss for me. I started last night as a quick check. Before I copied the data on the USB sticks, I said, oh, let me give it one last try. And I'm really happy I did, because I made a fairly big change in Last Tools last weekend, and everything compiled just fine, but when I tried to open the GUIs, they all crashed, because there was a small little change in include files. So last night at like 11, after we came back from the bar, I had to fix all this. And I'm really happy I did, because this would have been a complete nightmare presentation right now. if I had it found out this morning the very hard way. So just by pressing add using the wildcard, we instantly add all these flight lines here to the GUI. So we are in, just in case you missed the beginning, we are in the folder called, just like the institute where we're at, Ciencia. And then the data is in the strips_raw folder. There are 5 flight lines, so you can either double-click each one of them, or you use the wildcard and just say add, and it will add them all at once. So what I usually do first, I have a look at what it says right here. I see, oh nice, UTM 11. So they seem to have correct projection information, or if it's correct, I don't know, but seem to have projection information, and I'm not from here. If you're from here, you probably can tell me if UTM 11 sounds about right. Okay. And then, as I mentioned before, by just using the arrow keys, you can sort of go up and down. And if I do this while I'm looking at the contents, I can, for example, make sure that the point size is the same everywhere. So all these 5 strips use the same point type, the same point size. Just here in this line, the arrow. You want to make sure that all these are really from the same origin, you know. They're all processed with Leica software, I guess. And they were created, here you see the creation date. They were all created on the same day. At least that's what this entry states. I'm not sure how, you know, it's easy to overwrite with some wrong information. And they're all compressed because I compressed them so the distribution would be faster with the latest version of the last zip compressor. As I usually recommend, the first thing you do when you get a new data, you take a visual look at it. So also, you know, just pick one of these lines, and now maybe you notice what I did. Just pick any of them. I went to selected file only. This means the last viewer will only look at this one file. If you don't do this, it will load in all the files, and it's going to take a long time. But I just want to look at one of these files. View. And, well, the files are flat lines. It's kind of pointless, but it doesn't hurt. So you see I have minus input only a single of these files. I press start. Let me zoom out. And here's one of these flat lines. Clearly, let's see, color by classification. Oh, there is some classification in here. I'm not sure this is claimed to be ground classification. That doesn't look very good to me. If I triangulate that, that is the classification in the file right now, how we received it. That doesn't look to me like to be a very good ground classification. So that I don't know where this comes from. You know, that's pretty much like I received it. There are some classifications in the file, and obviously this is not a good ground classification here. So I pressed, to get here, I pressed GT, ground, and then triangulate. Let me look at one of the other ones, maybe this one here. Do the same thing, view, start. Again, do we have ground information? G, oh yeah. No, I don't think this is actual ground information because I don't know what it is, but it doesn't look very much like ground information, or at least not very good ground information. But that doesn't really matter because we were expecting raw data anyways. If you want to get rid of the triangulation, just press Shift-T. That's like untriangulate. And I press A to get all the points again. And then I press X to sort of walk through the points a little bit to get an idea what I'm looking at here. Well, clearly this is not ground classified properly. I don't know where these brown points come from or what they mean, but they are not ground, obviously. And then I can change with the coloring. Here you see I have a lot of single returns, but it's not too surprising because the area here is not very heavily forested. So the multi-returns are mostly along the buildings and the bar along here you very nicely see the edges of the building being hit once, and then it continues on and hits, you know, this grazing of building edges that we talked before. It's very nice to see here. And let me try one thing. I'm not sure it works. I didn't try that yesterday. But there's one option in Last Tools, which is in Last View, and I told you it's a bit of an experimental tool. To reconstruct the pulses, and this may not work at all. Let's see. Oh, it does. So whenever I have multiple returns, I can draw a line through these multiple returns because they are from the same pulse. Yeah? You see how they all converge to the same point? These lines are only, I basically draw a line through every multi-return. You see, whenever it's multipled, I draw a line. And you see these lines are not arbitrary. They are quite aligned, and I can make these pulses longer. 500 meters, I chose now. And, oh, not yet. So I choose the pulses to be 1,000 meters. And, yeah, I would say that plane was flying at about 900 meters. How cool is that? I just use the multiple returns. They gotta be on one line, right? The first, the second hit. And then I draw a line. And where all the lines are hitting, that's where the plane must be. And
how do you know it is 900?
Well, I make these lines, this is just a rough figure. I make the lines 1,000 meters long until they hit. And they hit, maybe it's 950. And they hit just a little bit before getting to 1,000. But it's I did not get information from Alejandro how high the plane was flying. With little trick, and that's why I say it's an experimental tool that has some little capacities which are kind of nice. In this particular one, we can get a rough estimate on the flying height by just taking all the multi-returns and trying to find where they intersect. And so in a way, this is exactly how you can imagine the laser coming down. This is basically the path the laser took to hit these two things, just by a reverse construction. And along these buildings, maybe with X I can focus on a smaller area. So if you want to ever try this on other data, it is important that the data is sorted by a GPS time for this to work. So the data needs to be sorted such that neighboring shots are stored together with each other. And the way to do that is last sort. If your data isn't sorted, this is already sorted because it's in flight line order. Last sort can sort by GPS time if you ever need to figure out how high your plane was flying and this information is not available in the metadata. That's one way of roughly doing it. Okay. So this was a little thing I hadn't really planned. I just sort of, thought I'd try it, and it worked quite well. So I don't know how good you guys are with the command line. I will show you a little bit command line quality check now. And the reason is I'm running one tool now that is only available as a command line tool. I don't know if you know how to get that black window. Does anybody know a very fast way of getting it? I know there's some. Yeah, but where do you type it? Yeah, but I don't have start. Windows R. That's it. Windows R. There you go. That's what I did it before, but I forgot the combination. So you type the Windows key on your keyboard if you have one, and R at the same time, and then hopefully you get this little box that allows you to run something. And then you just type command. And then something opens in some location. And now you need to go to where last tools are, wherever you drop that folder. I dropped it on the H drive, so I do H drive, and then on the H drive. If you can't follow this part because the command line is just too out there for you, don't worry. This is kind of an optional exercise. Nothing depends on it. Then I have it in the last tools directory, and then I go to the bin directory. That's where the last tools are. CD, that's the command to change a directory, change directory. So I first went to the right drive, H drive. In my case, I don't know where you have your last tools, maybe the D drive, maybe the E drive, maybe the C drive. And then I find my way to the right directory. And here's a tool called last validate. Last validate checks if your LiDAR files are correct, meaning not that the quality is good, not that there's a certain accuracy, not that the points are in the right location. It just checks, are the LAS files or the LUTs files actually valid according to the specification of the ASPRS? So it has the usual syntax, the input minus I, and then as an input I put my C there, and by pressing tab you can autocomplete. So I really only need to type CI and then autocomplete by pressing tab. And then I press slash strips raw. That's where my raw data is, but I really only need to type str and press autocomplete. And again a slash star. Star. Yeah, so so the next exercise will be to hack the Pentagon. That was a joke. In case, the Homeland Security is listening, this was just a joke. Because we are online on YouTube, it goes through Mountain View and everything. And now I want to get an output. So this will generate a validation report for each of the files. And the output I want to put in the quality folder. This is already created for you. This is quality. You see, I always use a tab. It's quite quick this way. And I'm going to call it validate.xml. It creates an XML report about every file. So last validate, the input needs to be, this folder, all the last files, and it outputs it into this report. And then I just press return. And this is the output I'm getting. That's a very encouraging output. I get 5 times a pass. So no fail. Too bad. Fails are usually better for, for the learning experience. But at least I give you a quick look at where these files are now. Huh?
When you fail, just sit and cry.
Yeah, that's what I do. No, but then you look at why they fail, and maybe it's a minor thing. Now I'm looking at the file we created. So under CCESA quality, there's now this validate file, and if I open this one, I get the XML file, which in this case opens with Windows Explorer, and for every file, I get a report. So I have 5 reports here, and the report tells me the name of the file, the path, and the coordinate system, and the summary is just path. There's nothing wrong with it. If there's something wrong with it, under summary, or under details, actually, under details, which we don't see here because there is no details to report, we will see warnings and failures listed. Why would this be useful? Well, if you, for example, use Open Topography to download the files, and in the middle of the download, your internet goes down for a brief moment, and then it comes back, you may have a few truncated files in there. You can't really tell looking at the file. You don't know how big it's supposed to be. This is a very common thing. Truncated files are very easily found by last validate. Or a bit flip may happen. If these USB sticks we got today to distribute the data, if I'm here in August and I put them in the glove compartment of my car and I go for lunch, and afterwards I give it to you, and it has been exposed to 60-degree heat, there may be a bit flip. And that bit flip may cause the decompressor to put a part of the points somewhere very far away into the, just corruptions. So bit flips, bus errors, transmission errors, USB stick is a very common source for bit flips, will be discovered by last validate. And then you have to go back to the source and get a new copy. This last validator is by no means the authority on last files. It is my best guess. And every time you run it, it will ask you, if you're not happy with the report and you think the report should be different, please send me an email and we discuss it in the group to improve this report, because it should be the most useful for everybody and not report false errors that are of no concern. So it will also tell you which version you used at the end and which command line you used. That's a useful starting point because it detects errors, especially, if you have 5 files, that's not a biggie. You can just hand check them. But if you have 1,500 files, that's a whole different thing. Okay, I hope I didn't scare you too much with the command line. Now, I still have last overlap open. I didn't close it. I don't know about you. If you closed it, then please load the files again. Last overlap. I just did a brief. Before I was running last overlap, I wanted to make sure that all my LiDAR files are correct. They all have the right, the bounding box is correct, the number of points is correct, they're not truncated, and anything other funny business is not going on. They seem to be proper. In order to do now the check, I first need to say process all files again. And now, these files that I have here are indeed flight lines. Hence, the checkbox, files are flight lines, must remain checked. Often you will be giving LiDAR tiles. If you have tiles, you cannot check this, because files are flight lines means every file is a different flight line, and the overlap between these files is where we're going to compute our differences. If you have tiles, there are no overlaps. Tiles are usually given without overlap. They are, sitting, they're all a butt to each other. If you were to press it, it would just produce this nonsense result. In every tile, there should be flight line information. However, unfortunately, not everybody is very good in preserving it like we do it later. We will preserve it, but not everybody does. If you don't have flight line information, there's the option to recover it. That only works if you have GPS timestamps. It will basically look for continuous flights, because a continuous flight should have a continuous number of seconds incrementing, without any gaps. And the gap happens when the plane flies out of the tile and comes back 10 minutes later. Then you have a 10-minute jump. And then it starts a new flight line. So it does two passes. The first one tries to find the gaps, and then based on the gaps, it assigns the points to different flight lines. That works very well if you have GPS timestamps. So not all is lost if you don't have flight line information. All is lost, however, if you have points in ASCII, in a format that does not populate the GPS times nor the flight lines. Then we cannot recover it. In our case, we have flight lines. So I'm checking this button. Everything else I'll leave in the default settings for now. Again, if you want to know the details, and I explained a bit of the details, but not all of them, they're in the README file. What I want to select is the output directory. We're doing this as a quality check, and just for this exercise, I put all my quality check materials into the quality folder. So I picked the quality folder, and I say use current. Now this result will go into the quality folder. Oh yeah, so I will merge them all into one file, and the files are flight lines, and then I get to pick a name here. It's already called overlap, but I want to use a different format. I always like to use PNG. And here it's already PNG. There are two ways of making the output. I can either make images for a quick visual check, and that's what I usually do, and only if something goes wrong I do more than that. Or you can produce the actual values as output. In this case, you produce rasters as output that have numbers 1, 2, 3 for every pixel, overlap by 1 flight line, by 2 flight line, by 3 flight line. That's for the overlap. This allows you, for example, to compute the amount of overlap between flight lines. How many pixels have a 1, how many pixels have a 2. For the difference raster, if you pick actual values, it will give you the actual value of the difference. That allows you to create histograms afterwards about the error distribution, an error histogram. Because sometimes it's allowed to have, like, in 5% of the cells, if the error is, it can be higher than 10 centimeters, but 95% of the time it should be below 10 centimeters. Those are typical quality requirements, and you can basically test them like that. We will do the color coding, which takes these differences and maps them to a color. It's important to know what the color means, and this is specified here. So a difference of 0.5 meter will map to a very strong color, either blue or red, depending on which direction the difference is. As before, white would be the ideal color we want to get. So if you want to be more stringent, you put 20 centimeters. Then already, if you have a 20 centimeter difference, you will get a red or blue fully saturated color. I just leave the default for this exercise. And I think that's it. I'm not entirely sure. I called it overlap.png. Well, I used a step that's already here. So maybe now is a good time that when I tell you what's going to happen. So what will happen with last overlap? It's going to put a grid over all the points. And the grid size is 2 meters. You can change that to be 3 meters. You shouldn't be too small. What it does then, it looks for every flight line individually, it looks for the lowest point in every 2 by 2 meter cell, in this case, 2 by 2 meters. So flight line 1, what's the lowest? It only does that in areas where flight lines overlap. It stores the lowest in each flight line. And then it compares the lowest of each flight line with each other. They should be similarly low because they're covering the same area. That difference is then reported. So if flight line 1 and 2 have an overlap here, in some cell of 2 by 2 meters where they have an overlap, I pick the lowest point in that cell from both flight lines, and then I report the difference between those 2 points. Very simple. And if the color coding is requested, I then color code that difference into an image. For every pixel, for every 2 by 2 meter pixel, I'm going to get 1 color. If the color is white, the 2 lowest points had the same elevation. And if it's blue or red, they had different elevations. Whether it's blue or red doesn't really matter. Just depends on in which order you give it the strips. If you change the order, the color just changes from blue to red. So I'm looking at my quality checking script run here. Again, list of files, we used that before. I have my 5 flight lines. I merge them. They are flight lines. I use the lowest elevation in every 2 by 2 meter step size. There is no minus step 2 because that's a default. If you use a different step size, it will say here minus step 3, for example. I put the output in this directory and I call the output that name. Intensity. You could check if the two flight lines have similar intensity. You could use the maximum number of returns to make sure the flight lines, and then you would maybe use a little bit bigger areas, that in the same, hitting the same forest, both scans produce the same number of maximum returns. I don't know many people who do that. I had one request once that I added more options. Initially, it was only elevation, lowest elevation. That's pretty much what everybody is using it with. But there may be reasons to do something else. Okay, it's done. And that ends our need for a last overlap. So I'm closing it. And I'm having a look at what I created in the quality folder. Oh, look, KML files again. Oh, that's nice because we had UTM-11 North information in the file. So I'm double-clicking, and I'm leaving Europe, and I'm going to, yay, Mexico. Here we are. Oh, we're close to Trinidad. Where's Tobago? Oh, no, that's a different Trinidad. Oh, I recognize the harbor. Yeah, we must be in the right spot. So we get a beautiful overlap image, as you see. So they really wanted to get a lot of points in this area. And Ciencia is right in the right area, covered by 1, 2, 3, 4, 5 flight lines. So we should have a fairly high point density if we, use them all right where Ciencia is. So now wherever we have a color other than blue, blue is just one flight line. We will get a difference image. By the way, you see how there's nothing where the water is. The plane clearly was flying over the water as well, because otherwise we wouldn't have LiDAR returns here, but we don't have LiDAR returns over the water. I don't know, it must have been, why don't we have LiDAR returns here? Is that also wet? Maybe that day it was wet? Well, it's kind of odd then. Maybe that didn't exist? Or maybe it has been removed since? Maybe, I know what, they use that painting, that really glossy, like last night when we were walking, they used that, it almost looks like it's wet, and maybe the lasers got reflected away, and I don't know, but there you go. You can try to figure out why we have LiDAR returns here on the pier, but not there.
So the LiDAR beams doesn't work in water?
It gets absorbed by water. It's infrared, and it just... The only time you get LiDAR returns on water, if the water is really, I don't know, really dirty maybe, with lots of stuff floating on it, or if you hit the water right from above, so you get a specular reflection, which you also get of the waves. It doesn't have to be from above, but it has to hit it at a 90-degree angle. But I've also seen, sometimes you get the water, I haven't 100% understood all the conditions under which you get a return from the water. There must be more. And the difference image. So you can clearly see there's a little bit of, flight line pattern visible in the difference image. Here we have a slight misalignment, and here as well, and here it looks like to me like a small horizontal shift, but not very strong. We don't have any very strong blue or red values. Overall, it looks very nice. But if you wanted now to make some analysis of baby carrots or like low vegetation, potatoes or peanuts, and you wanted to find, if there was a plantation of peanuts and you wanted to find if the peanuts are growing, then, and these peanuts are only 20, 30 meters high, then you may have a problem because you shouldn't be using these areas here because a flight line difference can create something that looks like peanuts because one layer is above the other layer and then you create points that are in that just above 20, 30 centimeters above the ground. So you use only the points from one flight line. That's what you do. We maybe have a look at this later. So we want to preserve our flight line information so that we can switch back and forth between flight line right in this area. But for the time being, we say, okay, that looks good enough. No dark red, no big blue areas. Okay, let's say this is for now enough quality checking. We could do more quality checking. Last Info is a tool I often use for quality checking, that it can print out an average density. Maybe we do that later when we have a tile, because it looks like the tiles will have very different densities. Some tiles will, where all the overlap is, will have a high density. Others will have a very low density. This is not a uniform density data set. We can already say that just by looking at the overlap. But rather than doing more quality check, let's do some more fun stuff, like starting with the actual LiDAR processing. For this, we want to use a tool called last tile. So I go to the bin directory, last tile. Tiles huge amount of LiDAR points into square tiles. Browsing to CSS, strips raw, add all of them. And we already have a suggested sample tiling in the background in green. These are 1 square kilometer tiles. It's a very common way to tile LiDAR because most point densities work well with 1 square kilometer tiles, and I suggest we just leave it at 1 square kilometer. However, in order to avoid artifacts along the boundary of tiles, what I always strongly advocate is the use of buffers. And the use of buffers. And buffers means we will make those tiles a little bit bigger than we need to. So every tile will be a little bit bigger. And we process everything with these bigger tiles. And along the edges of these bigger tiles, we will introduce errors. Errors in the classification, errors in the height computation, errors in the interpolation. But that's okay, because in the very end, we're going to cut off those buffers and only use the original tile, the 1,000 by 1,000. So we will add a 25 meters, which you can see shown here, 25 meters around every tile. Anybody bake cookies for Christmas? Anybody? I used to, with my mom, bake cookies for Christmas. And you roll out the dough, and then you have these little stencils, the cookie cutters, and you cut the cookie, right? Now, when you come to the very end of the dough, you know, when you're a kid, you want to get that one last cookie. But that one last cookie, you roll it out, but it's not, it goes all the way to the edges of the cookie. So you cut it out, and then you have slight artifacts along the edge of the cookie. And that's exactly what you get with tiles. So you want to roll out the dough, and the dough is our tile, big enough, so at the end, when you take your 1 kilometer by 1 kilometer cookie cutter, you have enough stuff that you can, you know, cut off. So all the artifacts of rolling out the dough, you know, it's not very smooth, is sort of in the stuff you cut off. And so we're going to make the biggest Christmas cookies. Well, it's more like an Easter cookie at this time. That's a very, very intuitive way of thinking about it. And it will be of relevance among all the interior boundaries whenever we have two tiles coming together. That's where this will play a role. We cannot do anything on the outside boundaries where we don't have data anymore. Okay, the other thing we need to select an output directory. I already created that for you. It's called, if you go up one directory, you see tiles raw. So when you press this button, you should be in this directory. You go up one directory and you see tiles raw. And then you say use current. And that's where the tiles will go, the tiles with the 25-meter buffer. And the default name for tiles is tile. That's not a really nice name, especially if you plan to work for many years with LiDAR. Because in 3 years, you find that thing again, it's called tile something something. You have no idea where it was. So I always advocate, think long term. Give it a nice name so you know where it is. How about Ciencia? Now every tile will start with the name Ciencia. You see that tile, you instantly know where it is. I especially told that to people that process many provinces over many years, like the project in the Philippines I talked about earlier. So maybe you noticed the name of these strips here, 3, 4, 8, 23, 26. These numbers at the end are most likely the strip flight numbers that are part of the flight planning software. So somewhere at NCOM, there is a metadata creation, blah, 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 where it says, you know, first we fly this flight, and this flight, and this flight, and these numbers there are 3, 4, 8, 23, 26. Associated with this are probably things like GPS trajectories, aircraft speed, times, you know, IMUs. Somewhere this data probably exists for a few more years, or maybe forever, I don't know. These are the flight line numbers, the original flight line numbers. And they're actually in the file. They're called the source ID, and they're right here, 26. This is a nice data set because it has the right number at the right place. You see, 26, 26, 23, 8, 4. Very rarely do I find these correctly populated. Very nice to see it done correctly. So that means instead of just saying files are flight lines and saying the first file gets flight line 1, the second file gets flight line 2, we will preserve these flight numbers, these original ones, because they can be attached to information that's available somewhere about the actual flight. So the way to do that is not only are the files flight lines, but we want to use the file source ID, because every file is a flight line, and the file flight line ID is stored in the header of the file. So I'm going to use this number instead of using 1, 2, 3, 4, 5. And this way, when I ever have to communicate to NCALM and get some extra information about this particular flight, I can tell them which flight line. It's a little detail, but especially for large projects, it can make a, where you can't just, oh, I just run it again. Yeah. So, is there anything else? I think that's it. So I need to close my output directory. So I see my run button. You probably have to do the tab trick again. And I press run and review my command line. So here I got my 5 flight lines. The output should go into, where's the output directory? Here's the output directory. I'm applying file source IDs. I use a buffer of 25 meters. I compress the tiles. Yeah. Looks good to me. Start. So it will read now 1, 2, 3, 4, 5 tiles, and every time it reads it, it goes into the points and gives them the point source ID of every point will be set to the file source ID. So afterwards, this information is still available in the tile. Every point will either be a point 3, point 4, point 8, point 23, or point 26. That number is written in the point source ID. So file source ID, point source ID. You get the, an entire file has one ID. In the other case, a single point has one ID. And I'm done. So I can leave last tile and have a look at what I created. Or rather than have a look what I created, I already load the next program. And in this case, and then look at it. And in this case, let's use last ground new. I'm not going to tell you here much about the difference between last ground and last ground new. Last ground new is still a bit sort of in development. I want to make it a bit better. If you want to know about the difference, read me, but I want to see if it works everywhere well. And I hope it will. So last ground new is just an improved version of last ground for certain complex terrains. For more details, see the, but it's a very similar algorithm. So I'm browsing now to CICESE, and I'm loading my raw tiles. So from now on, we're going to operate on tiles. And here are my tiles. This is the naming of the tile. The name of the tile is the name we wanted, CICESE, and then lower left X, lower left Y coordinate. So that's the lower left X coordinate, and that's a lower left Y coordinate. So you look at the tile and you instantly know where it is in your projection. Actually, you could create a bounding box for that tile just by looking at the file name and knowing which projection it is. So I'm adding them all. And instantly you should notice the overlapping buffers here. Or actually, one thing I usually do is, I meant to do this first, have a look at what was created, tiles raw. Because sometimes you create files that are not super useful. Like this file here. It has a size of only 1 kilobyte or less. And if I look at what's in this file, in this particular tile, it has it has 2 points. So we got so lucky. We had a tile that was just at the boundary, and it got 2 points. We may decide just to throw out that tile. One idea is to sort by size and just delete it here, but I already loaded it. So the other thing to do is we can just use our menu and look for that file. Oh, there, I was lying. It has 3 points. So you see that file, the first one has 3 points. The next one has a lot more. So these all have a reasonable amount of points, except the first one. One way to get rid of that file is just go on that file and press delete. And now it's not part of our tiles anymore. It's still on disk. I didn't delete it on disk, but now we're going to ground classify it. And after ground classifying, it will not be part of the ground classified output. You don't need to do that. If you didn't do it, it will just get copied into the next directory. But it's kind of I usually throw out these little files because they won't contribute in any meaningful manner to the final result. Okay, so what did I do? I think I just leave it on city. And I leave the default mode as well. I compute height, remember, so I can classify it later. And I select an output directory. And if you look at the folders I created for you already, that would seem a reasonable output directory to choose. Tiles ground. Use current. And now I have, yeah. So why did we even tile it in the first place? Why didn't we just, do it all in one file or merge on the fly or so on? Well, there's a certain memory limit to what LastTools can handle. 20 million points is about what LastGround can maximally handle. 20 million per file. So that's one reason we need to cut our LiDAR into tiles with buffer. Because cutting it into tiles only will create artifacts. Not cutting it would not create artifacts, but would be too many points. So cutting it into tiles with buffer allows us to have smaller parts without getting artifacts. It also allows us another thing. Most of you will probably have more than one core on their computer. By cutting it into independent pieces with buffers, we can now run in parallel. Instead of just running one LastGround algorithm, I can run 4 or 6 or 8 at the same time. This claims to have 8 cores. It really only has 4 cores, 4 dual cores. So I choose 4 cores right now. But I haven't really done the time measurement. What is faster, choosing 8 or choosing 4? This will basically give the first tiles of the first compress, and it will distribute the tiles one by one. And if any tile is done, it gets the next tile. So you will have 4 processes running at full speed, trying to ground classify the data. That's another reason to do tile-based processing. You can exploit the trivial parallelism that you have once you have independent tiles. So do not use more jobs than you have cores. That makes no sense, because then they will just fight with each other for the resources and slow everything down overall. If you want to still, update your Facebook status while it's processing, run on one core less than you have. And that's why there's the option cores -1, your number of cores -1. Otherwise, it'll take you forever to upload that cat picture. So I'm running last ground new on all these tiles. If you're running last ground, it's no big deal. It should work just as fine. I have the option compute height. I output it into the ground directory, and I output compressed. And this command here, -cores4, means if there is more than one file to process, it will be distributed on multiple cores. If you press start now, then, like for me, the fans are coming on instantly. And you see in the black control window, lots of things, lots of parallel outputs are happening.
What do you call the output?
How do I call the output? Console output. How do I get to it? I press Alt-Tab until I see the black window with lots of text going by.
How you name the output?
I didn't name them anything. They keep their name. But good question. I didn't name them differently because I'm using a different directory for output. I'm going from an input directory that's called tiles raw to an output directory called tiles ground. The names of the files in both directories will be identical. It is the name of the directory that tells me the difference between them. I cannot, of course, use the same directory, then I would overwrite the files with themselves. How do you know you're done? When the menus become active again. And looks like I'm done already. How quickly you're done depends on your settings, on your computer, obviously, on the number of cores you're running on. Yeah?
When you use the merge switch, the overlap is just done for the...
Overlap can handle a lot of points. Overlap has no problem with memory because it uses an out-of-core memory handling. What was that question related to? Yeah, so merge switches only work in programs that are very scalable in terms of memory. Those are last grid, blast to them, the blast extension of last tools. If you want to know more about the blast extension, go to rapidlasso.com/blast. Blast is basically the PhD that got me into LiDAR, implemented as extension to last tools. 1 billion points triangulated into a big tin and then on the fly rastered into a gigantic DEM. That's blast. We don't use it today in this course because tile-based allows you always, I have a client with 42 cores. He doesn't want to use blast, runs on 3 cores. He wants to make many small tiles and run on 40 cores in parallel. Tiles are nice. They give you parallelism, very trivial, very robust, very efficient parallelism without any inter-process communication. Once the tiles have a buffer, you cannot merge them anymore. Otherwise, you replicate the dirty buffers, The buffers have the dirt. If you merge buffered tiles, you have multiple copies of every point in the tile, a good one and a bad one. And They do warn you when you try to merge multiple tiles with buffers. So let's switch directly to the next tool because slowly time is progressing. Let's classify it. Last classifier we ran before. Last classify, finds buildings and trees. Let's hope we find some buildings here at Ciencia. So I need to use as input my ground classified ones, and that should be now one less than before. The little one with 3 points, shouldn't be there anymore. And well, let me see. Yeah, I don't think, no more 3 points. Okay. Again, I'm running on, oh, no, actually, what I want to do now, of course, I want to have a look before I continue. Maybe I have a look at this one. And only at one file, remember, when you want to view, you don't want to view all of them, selected file only. Now, everything will happen only on the selected file. So before you do last classify, you must go to all files again. But right now, I just want to look at one of these files. Yeah. Well, that ground classification certainly looks different than the one before. And I say T like triangulate. And that's so I'm not sure about this one, if that's a building or not. Maybe I should have run it with one different, with metro instead of city. You tell me, or we look at it later. But okay, I mean, we definitely have something that looks like a nice ground. And so we run last classify just in the default mode. Process all files, run it for a course, and now the only thing we really need to do is the output directory. And we want the classified tiles. Again, I did only 3 changes. I process all files on 4 jobs on 8 cores, or for you maybe 2 jobs on 4 cores, or 4 jobs on 4 cores. It doesn't really matter. And I pick the output directory, tiles classified, and that's it. I say run. And I make sure the tiles are really the ground classified ones, yes. And I press start. And again, the name will remain the same. We now go from the tiles underscore ground folder to the tiles underscore classified folder. Sometimes I do denoising first with noise, last noise, which we haven't done today. I saw some clouds. We probably can cut off those clouds with last height, which we may have to do before we create a DSM, because otherwise these will be funny artifacts in the DSM. So these tiles, also their name suggests they are only 1,000 by 1,000 meter. They all have still buffers, meaning they're really bigger. And you can see these buffers in the overlap between the tiles here. We will cut that off eventually. So my last classify is done. And maybe now it's a good time to run last noise. No, I don't really have a folder for that. Yeah, let's only do that if we have extra time in the end. And I see the time is progressing. Let's make the DTMs. The DTMs will go in the tiles_DTM directory. And you should remember which tool we used for making DTMs. We did it already, well, once at least. And then second time we switched to the scripts. Last to them was a tool. And there will be one important difference this time in last to them. So first we're going to create a DTM. For the DTM, we need ground classified LiDAR files. So which input folder should I choose? I could choose last classified, but I can also choose last ground, because both have the ground points already classified. It doesn't matter. The only difference of last classified, it should also have vegetation and buildings classified. I choose classified because I want to also look at the classifications with last view. Maybe let's look at this one now. Selected file only, view. So here's my classification. I'll have a closer look, walking through here. That looks okay. It's a, well, what we got here? We got vegetation next to a building, but that, here it looks like that made a mistake. I mean, there's a big step somehow. I don't know where this is. So it decided, oh, look, it's 2 meters above the ground, so it must be a building. But no, not really. I don't know what this is, a balcony or something? Or maybe it is part of the building. It's a roof. Yeah, we'll and These things, I'm not sure these are really vegetation. It looks more like, I don't know, a bus, like a little gazebo or something. So there are several, oh, this certainly doesn't look like, or maybe, I don't know what this is, a very noisy roof. Or like, no, maybe it is some kind of, how do you call these things which I have in the gardens? Like where they grow the vines on, like a trellis? Yeah, right. That would look like a vegetation to the last tools algorithm because, you know, it looks for things which are very not planar and are above 2 meters. That's basically the algorithm. And what we got here? Tall palm tree. So there are a few parameters you can play with if you don't like this ground classification. Oh, I remember there was some issue with flight line alignment, right? I think it was maybe even in this tile. So do we have flight lines? 0, 1, 2. Oh, yeah, we do. 0, 1. So we have 2 flight lines here. And they're even in opposite directions. One is left, right. I mean, they are perpendicular to each other. So now this is a good place to make a flight line check, just sort of a visual one. So I pick an area where I have overlapping flight lines. Like here. I have the green and the red one is overlapping. Or not just the green and the red, I have a lot of flight lines overlapping here. And I have 0. And let me walk to an open area like 0, 1, 0, 1. Yeah, so now I can triangulate this one. I triangulate the 0 flight line. And then I select the flight line 1. And look how these points match up with the other flight line. Oh, they're above and below. That's pretty good. How about the next one? 2, 3. Above and below. That's always a good sign if they show up above and below. Okay. Maybe that was not the bad part, because that looks pretty nicely aligned. You know, I picked one flight line, I triangulated it, and then I compared all the other flight lines against it, and they're all in very close proximity to the triangulation of the first flight line. This is the flight line I used to create the triangulation, and then I compare it with this, above and below, this. No, this doesn't exist. Then we can decide to triangulate a different one and show the others. So where was this area where we got red? Oh, it was here. So that's the next tile, one tile over. So I think it's in this tile here. So I have a look at this tile. I'm turning on the visualization for the different flight lines so I know where I have overlap. Now I compare this to this one. Ah, yeah, it's where the east-west and the north-south strips overlap. So that's right here. So I'm picking an area from here. Oh, and it's nice and open. So I pick this one, I triangulate it. Open field. But I have some kind of shrubbery growing there. That could, of course, be the culprit. Yeah, so let me take a bit smaller portion. One way of comparing it more exactly is to, yeah, it's a very rough surface here. I think there's some kind of a low vegetation growing that is seen differently from different angles of the scanner and then creates these, so I can triangulate, for example, this surface here. And now I pick a different flight line and I hang something I call drop lines on every point. And these drop lines I selected in the menu, drop lines, are 0.5 meter. So I hang a 0.5 meter line on every point. And if you have a flight line misalignment, you will see every point is about the same distance above every other point. Like if you have a flat surface, like a road, and then the points from the other flight lines all have sort of a 15 centimeter drop line until it hits the triangulation and disappears. See, the majority of the drop line you can see below. That's the most of the 0.5 meter you see from below, and it's very irregular. So I think this may have to do with the vegetation on the ground, that the laser has different penetration depths depending on how it was shot. That would be, just from this little analysis, my guess. And I wanted to show you the drop lines as a way of examining this a bit further. Okay. So we are in last to them. We want to make DTMs. So let's do the easy stuff first. Process all files. Now I get bold. You know I'm going to run on all 8 cores. I'm outputting it to the tiles DTM directory. Oh, we didn't check the density of that data set. Oh, that's usually, I meant to do that, I forgot. Do you know? No, the density. How many points this data set has? Okay, well, let's do a quick check. So I show you how I quickly answer this question. I just have this question. I don't want to really do a lot of work. I go back to selected file only. I pick this one here. This one, one of them has a really high density because it's so many flight lines. This one is sort of in between. Down here it has super high density, up here it's a little. I press last view, and now I'll show you a little trick. It's supposed to run last view, right? But I really want to run last info. Info. I want to run last info. So I just changed the tool I'm running. And the particular thing I want to do, I want to compute the density. So I tell it minus CD. This option will play your favorite music while it's processing it. No. It's short for compute density. And it's an approximate density. But for our purposes right now, that's sufficient. So it will execute whatever you write in this command line. So I suggest you do not write the command for format my hard drive in this, because it will execute it, or delete every file on the disk. It is just taking whatever is written there and executing it. I shouldn't have told you that. Oh, and it's live streaming. Oh, man. Oh, man. So in the black box, that is in the black control window, we now have our result from the last info run. Point density, all returns, but the all returns is not the important one. In this case, we have very open areas, so last only and all returns is almost identical. We have 6 shots per square meter in that area. So maybe we can do a half meter DTM. Of course, in the areas that were a bit farther off, we have much less. But yeah, so let's do a half meter DTM. I go back to my tool, process all files, half meter, 0.5. We could do actual values, but hillside shading is more suitable for this kind of interactive workshop, where we don't want to start a QGIS or ArcGIS to do then the post-processing of the rasters. The output format, therefore, is PNG, because it's going to be, again, a picture. We're going to store it. I think I already specified into tiles underscore DTM. I select this already. And again, we need to filter, remember? It is with 2 feet we stand on the ground, so we need to filter by classification the points of type of class 0, of class 2. Keep classification 2. And now the most important part. Christmas cookies. Now we're doing the cookie cutting. We have a 1,050 by 1,050 meters of LiDAR data. And the 25-meter buffer around it, that's where all the errors are. And we want to cut off this and only use the real tile bounding box of 1,000 by 1,000 meters. And it's as easy as checking this box. Use a tile bounding box. That means we will create a tin with all the points, 1,050 by 1,050 meters. So that tin will pretty much look like the dough we're rolling out when we make the Christmas cookies. It's going to have fuzzy edges, because it's going to be a convex hull of 1,050 by 1,050 meters, with the elevations and the ground classifications not being so precise along the boundaries. And then we take our 1 square kilometer cookie and put it right in the center, so that there's a 25-meter dough, LiDAR dough, sort of getting cut off everywhere with a very clean edge. And we do that for every tile. And the resulting tiles will fit perfectly to each other with hopefully no artifact across the boundaries. So let's look how this command line looks then. So there's now a whole number of tiles that we will turn into DTMs. I'm boldly running on 8 cores now. I keep only the ground points, step size of 0.5 meter, hill shading. We use a tile bounding box. That's the command. So basically, during tiling, we say minus buffer 25. And final step, when we create the DTM, we add this command. And these two work sort of, hand in hand to avoid edge artifacts. And the output goes into the LiDAR DTM in the PNG format. And it's done. So you will know that you used the cookie cutting when it talks here about clipped rasters. These are the triangles that are hanging sort of half into the tile, half out of the tile. And let me give you one image that I took in the Philippines to explain why I think this is very important. It was at UP, University of the Philippines in Cebu. That's the picture. Okay. So I used their calendar for the tiling. What you see here is a tiling in the background. And then I drew one tile in the middle here, this one. I drew in black all the ground points. You see all the ground points in black. And then I triangulated all the ground points. And first we're going to look at this side, not using buffers. So if I triangulate the ground points, I get a convex hull. And that convex hull doesn't go quite all the way to the edge of the tile. That's the first problem. So I'm very likely to end up with empty pixels, unless there happen to be a ground point right in the corner, which sometimes happens, but not always. So you will end up with empty pixels if you don't have buffers. The other thing, you get really skinny triangles. Like this triangle here, it goes from here to here to here and back. It's like a sliver triangle. Now, if you interpolate along a sliver triangle, you get very poor interpolations, because ideally we have nice and round interpolation elements, as anybody who's working with interpolations knows. Now, in the middle of our triangulation, all the triangles look kind of nice and round, but here at the border, they can become really long and not nice. So the idea of buffers is, let's use the points from the neighboring tiles, like here. Here I use buffers. I use this point from that tile, this point, this point, this point, this point. They really belong to another tile, but I'm using them. The result is I get nice triangles all the way to the edges. Everything is covered. And the triangles that are covering the border here, they have the same shape as the triangles in the middle, so there's no difference. And that's how the artifacts get avoided. I don't use, and these are the clipped rasters. This triangle here pokes into here. So maybe I use this raster right here. I make it a raster. But most of these things of this triangle are getting clipped because they are not part of this tile. I'm only using this triangle to make the interpolation of this raster here just as nice as the interpolation of this raster in the middle. That's sort of a intuitive, a bit, beyond the cookie cutting explanation. Okay, so we should have DTMs. DTMs? Oh, here they are. And if I sort by type, now I can drag and drop. So here we are. That's our DTM. And where are we right now? Somewhere here? I think, right? Huh. Okay. Okay. You can also, of course, directly look at the images. There's all PNGs. In your favorite image viewer. And that's... Hmm? Yeah, so in these places, of course, where it looks not so nice, that's where the buildings used to be. Okay, now it's 4 p.m. I think we're going to do the rest after the coffee break. Is there a coffee break? I wasn't sure. Okay, there's a good. Oh, we got a question over there? Well, LAS ground finds the ground points. LAS classify only looks for buildings and vegetation once you found the ground points. So it's sort of an add-on. Because I'd say, 80% of the people only really want to know the ground points. And, all right. In the first version of LAS tools that had ground classification, LAS ground was actually called LAS classify. Because I thought, that's all I'm ever going to do. But then I created LAS classify, and then I thought, what am I going to call LAS ground now? And then I call it last ground. Okay. I'm ready for some coffee. And when we come back, we will filter the noise and make a DSM. And yeah, and maybe that's already it. We get to the end. Maybe then we look at full waveform real quick. Okay. Enjoy the break. I think 20 minutes again. So I'll see you at 6:20, 4:20. It looks like we lost internet. When I lost my internet, we lost the streaming.
There's no internet, right?
I think so. And that probably means we weren't streaming anymore.
Wo haben Sie geboren?
Wo ich geboren bin?
Ja.
In Frankfurt.
Sind Sie Schwabe?
Nein. Nein, um Gottes Willen.
Das ist ein neues Wort für mich. Ich habe in Mexiko-Stadt geboren, aber ich habe in die deutsche Schule.
Okay.
Está mejor tu español que mi alemán.
Oh, wow.
Pero,
How long did you live
in Mexico?
in Germany?
No, never. Never been in Germany.
Oh, okay. Wow.
But Mexico City has the German school. It's like being in Germany. The chalk is German. The cake is half a strudel. It's houses like that. Christmas is also German.
All right. I should close a few windows. So, before I forget it, I've been known to forget it. So, one other thing when I was in the Philippines, I learned there is they have this tradition of when somebody comes from somewhere to someplace else, they always bring something from the place they're coming from. They have a word for this. I don't know if you have a word for this in Spanish. Anyway, we have sort of a word for it, but it doesn't quite fit it as good as a Filipino word. It's called pasalubong. Does it make sense in Spanish? Pasa sounds Spanish, but lubong, not so much. Anyway, before I forget, and everybody runs off, if you stay till the end, I got German chocolates. So, don't go away. All right. So the next thing we wanted to do, I think, was DSMs. Now, we did have clouds in those tiles, in some of those tiles. And I didn't create a folder for what I should be doing, is namely denoising. So I'm going to create one more folder here, and I will call this a new folder in the same directory where I have the many folders already. I will call this tiles denoised, or you can call it whatever you want to call it. That's where we'll put the tiles after removing the clouds, declouded. There are two tools. One is good in removing isolated points, and one is good in removing clouds. The one for removing clouds is last height. And you can say, remove everything that's higher than 40 meters, assuming there's nothing, there's no skyscraper or no crane or no tower that you would remove as well, or 50 meters. Because the other tool is last noise, and that can remove isolated points. Now, removing of isolated points does not always work for clouds, because if you have dense clouds, they are actually not isolated. They can be quite like an object, just really high. So that's why these both tools exist. Maybe we first try last noise, just because it's a tool I haven't really used much in tutorials before. And so this is a bit experimental now. I haven't tried that myself. So there's a tool called last noise. And so before you start the tool, make sure you turn down the volume of your computer a little bit. No. Okay, the jokes are getting worse. So let's load the classified tiles. So what last noise is doing, it puts a grid. You can decide to put a grid over these points, and the grid can be different in X, Y, in horizontal direction, and in vertical in terms of resolution. And then you tell the tool at what point something is isolated. So the default, let's just run the default first. The default will say everything is going to be gridded into cells that are 4 by 4 meters wide and 1 meter tall. Meter. Nobody uses feet. Feet is, yeah. Yeah, I don't know. UTM is meters, and I think the heights you use are also in meters. So we're putting a grid, a three-dimensional grid over all the points with sort of flat cells. They are 4 by 4 meters and 1 meter high. That's what these two parameters specify. And now we say the points in the cell will get classified as noise if this cell and all the cells around it, these are 9 cells on top of it, 9 cells on the bottom of it, and 8 cells around it, so it's a 3 by 3 neighborhood of cells, contain only 5 points. That's what the last parameter says, isolated. And now you can play with these parameters until you get the right noise removal. So you look at every cell. That cell has 20 points. Oh, then I don't need to look at it any further because it's definitely not isolated. Now I find a cell that has 2 points. Now I look at all the neighboring cells. If there are no more than 3 points in the neighboring cells, then these 2 points are classified as noise. Or if there are 5 points in here and nothing in the neighboring cells. That would be the conditions. And then you move on to the next cell that has less than 5 points, and you do the same check. You have the option to remove the points or to classify them as noise. If you remove them, you can't really check how good the algorithm works because you don't see them anymore. You don't know if maybe too much has been removed. So I usually use the classify as noise option, which is the default. Instead of running on all tiles, it makes sense to run on one tile first. So selected file only. But I already want to put it in the right output directory. So tiles denoised. So I left all the defaults. The only thing I changed is the output directory. And I say, let me first run on one tile. I say run. Start. So I think you will have to open some kind of new tool and go into the viewer. In my case, I just need to double-click the file because the default uses last view to open them. So the noise points will be, and I can, if you press N, you get the noise points. And if I press A, I get all of the points again. So clearly the clouds are not gone because they are too clustered. That's what I meant before. The points here aren't really isolated. The clouds are almost like solid objects in the sky. They're fairly isolated. That's why a lot of them have been classified as noise, but not entirely. Let's look what the last noise did here. Or maybe let's go in the overlap. So you want to make sure you don't remove too many points. So here are the noise points, all. And yeah, that's sort of points on like thin poles. Maybe there's a little cell tower here. Now here's like a, I don't know, it's a street lamp maybe. So you will also lose a few very sparsely sampled features on the ground. So that's one way of doing it. And I say, yeah, we don't really lose too much. You know, I don't see a lot of false things getting removed on the ground. A few street lamps. Yeah, okay, I don't care too much about the street lamps. So I want to remove now the noise points to create a nicer DSM. And the DSM should basically contain all kind of significant objects on the, you know, in the terrain. All the vegetation, all the houses, but not necessarily the cables. Now, last noise will not remove all of the cables. I'm still working sort of a little bit on that. But if I look at the things that get removed here, these noise points, I can live with that. That's all little stuff. And if that's not in the DSM, it's okay. I'm mainly interested in the houses, and the vegetation should remain there. So that's good. I didn't remove too much, but unfortunately I still have, you know, I still have the points, I still have the points in the top. Of course, you could go and manually remove them. But I think in our case, it'll be a two-step process. So I will remove these kind of points, these kind of noise points. But I will do a cloud removal. So I say I'm happy with this kind of noise removal. So I now apply this to all the tiles. I just say process all files, and I run it on all 8 cores. And I say run. The only difference, instead of running on one file, I run on all the files in parallel. But of course, it didn't really solve the problem yet. We still have the clouds. And the clouds we will have to remove because they are solid objects. I could now go and say, oh, I'm going to remove everything isolated 15. But then you're going to lose features on the ground as well. So instead, I want to use last height to cut off the clouds and say, now in the second step, everything that's above 50 meters, mark that as clouds too. Then I get rid of the isolated points as well as the solid clouds. Of course, it also means I need to create another directory. Because I was hoping the clouds weren't that dense, but they are. So I create one more folder called tiles declouded, or whatever you want to call it. So maybe one more check of the denoised ones. Looking at a different one. No. So you may decide that this is too many noise points removed, and you want to change your parameters a little bit. I told you what the parameters mean. If you read the README file, it'll explain it in more detail, but we don't really have the time today to make several iterations to find the best possible set of parameters. So I'm just going to say this is good enough for me. Maybe in reality, I would maybe change the step Z to 2 meters, then I wouldn't lose the poles. But I really want to get rid of the clouds now in the sky. And now I do my last tool before I create the DSMs, and that will be last height. And we will use last height now in a different. We didn't really use last height today. We ran last height as part of a batch file. So now I'm loading my noise removed points, and as output directory, I now specify the declouded. How you call your directories, you can give it Spanish names, sin nubes, right? Denoised, yeah, because I want to also now keep the little, because I also noticed earlier that there are individual points all over the place, which I don't want, because each of these points in the DSM will be one spike going up. So this is last height. Compute the LiDAR point's height above the ground. It will use the ground points, that's okay. And now you have various options. One thing I didn't talk about today, if you want to normalize your LiDAR, meaning making the ground points all 0 and have normalized LiDAR heights, then you use this check box. This is usually what people do that want to work with vegetation, do vegetation analysis. However, we just want to drop point, or actually we want to classify points. Everything above, I'm just going to use also 7. 7 is usually the noise class. Everything above 50 meters, I should really check that there's nothing higher than 50 meters in my acquisition area, but I stood on the balcony, I sort of looked around, I didn't really see anything that's really high. So 50 meters would seem okay, unless the clouds are very low. Maybe the clouds are only 40 meters, and we won't remove them. I don't know, so what's the highest thing around here? Any guess? What's the highest thing above the ground? 20 meters, 30 meters? The palm trees, how high are the palm trees? 15? No more? So maybe we can go down to 40 meters. So everything that's higher than 40 meters is probably going to be not part of any man-made object or any plant. It's going to be a bird or a cloud. The bird should have been removed with the last noise, not removed, classified as noise, but the clouds are not yet. So that's it. We're only going to use this option here. Classify everything above 40 meters as noise. And the output directory I already selected, and I'm going to run this on 8 cores. Well, actually, yeah, it's so fast. If I had 500 tiles, I wouldn't run the entire data set. I would first try on 1 or 2 tiles that contain clouds. So that's the command line. 8 cores classify above 40 to 7. 7 is the class for noise points. And it's already done, and now because I know I really wanted to create the DSMs without clouds in them. I go back to last to them, and I now load my declouded ones. Tiles declouded, add, and I think cloud, which one, this one? This one or this one? No. This one? No. This one? Yeah. Okay. No? Well. All right. My clouds are pink now, and you want your clouds to be pink. Now we got them. So everything that is not really on the ground is certainly a noise, and if we have a few more. Oh, what's here? Ah. You know what you got here? That's an edge artifact. Because it's on the edge of the tile, exactly on the edge, and the ground in this area is I guess I picked the wrong one. Oh, yeah, here we are. Why are they all noise points now? I can show you why. Ground, triangulate, and here we have a classical edge artifact. Huge triangles. And I don't have any ground information here, so I use whatever is closest ground, and it's not the real ground. It's because it's an edge artifact. So I get very high heights here, and that's why I classify it as a cloud. But I'm cutting that off. That's in the buffer. So no problem. Okay, so now I think I can compute my DSMs. And I do that in the following way. I say, I'm only keeping the first returns, as always, but now I'm dropping all classifications that are noise. So if the first return is a noise point, I'm not using it. So this is two filters. Again, both these filters are, how do you say, permutative. They can be permuted without the result being different. This is commutative. That is not the case for all filters. In some filters, the order in which they are applied makes a difference. And that's the only time, really, when the commands you put in the command need to be in a particular order. The first listed filter will be done first. And this thin with grid filter or keep random fraction filter, these are very typical ones which are very sensitive towards the order in combination with other filters. That's all I want to say about this right now, because we didn't use it today, but something to keep in mind when you filter with these filters that are not commutative. Okay, so we have the right filter. We want to put the output into the DSM directory. We apply, again, a hillside shading, and not to forget, the cookie cutting. And I need to close the output rollout to see, and the format needs to be PNG. Well, let's look at the command line to see if everything is here. Oh, made a mistake. I didn't use all the files. So I say cancel, process all files, and also run on 8 cores. So run on 8 cores, process all files. Oh, you see there's also this option, run on all -1 cores. And that's going to give you 7. Oh, the step size also, I forgot. 0.5 meter, so it's the same step size as the other one. I think now I have it there. That's why reviewing the command line is useful. So my input files are the declouded ones. I use 7 cores first only, and then I drop everybody with class 7. I use a step size of 0.5 meter, hill shade, use tile bounding box that does the cookie cutting here. And it goes into the DSM directory. The bounding box is stored as a variable length record inside the LAS or LAZ files. If you do last info, you will actually see it. It's called last tiling, and it contains the tiling information. So that only works if you use last tile to generate the tiling, because only last tile generates that. Well, it generates that information. You know, you can use other software to generate the buffers, but then last tools won't have the information how to what the buffers are. Or what the original tile size is. So keep tile bounding box is meant to work in conjunction with last tile minus buffer. There's another option. If you get already tile data without buffers, there is a way of also doing it called on-the-fly buffering with last tools. If you want to know more about this, go to the Last Tools Facebook page and check the Phil Leiter Dream Tour, because we had this issue all over everywhere. They got delivered tiles which were already classified and then created DTMs from them without buffering because they already were classified. And there's a concept of on-the-fly buffering in last tools, which isn't really documented yet. It's a fairly new feature. But it's super well documented in this 170 pictures in the Philippines with a lot of command lines and examples and showing what happens when you don't have buffers and so on. Some people say, oh, why you put it on Facebook? That's not very professional. Facebook is so popular in the Philippines, and all these young scientists, are between 20 and 25. They're all on Facebook all the time. So by putting it there and then mixing it with social pictures of eating, taking group pictures and singing karaoke, and then tagging everybody, it was a greater chance that people were actually going there and also looking at the technical ones. So as filters, I used first only to keep only the first returns, and then I'm dropping class 7. 7 is because that's what the noise class is. Why is 7 noise? Now, I had the example. 2 is ground because we stand on it. 6 is building because people live in boxes, and boxes have 6 sides. 7, why is 7 noise? Somebody have an idea? 7. Yeah. Did you get it? From So now we should have here they are, the resulting tiles. Okay. Parking lots. So where are we right now? Huh? Yeah? This building? This one? Oh, and they didn't have this building yet.
Not yet. It's built in 3 months.
Oh, I see. So maybe let's... So we can compare. This is the DTM and the DSM, computed with last tools. Did it remove everything correctly? Well, I think it's pretty much exactly what I would remove if I had the choice manually. Or do you see anything wrong? Maybe this thing should be really ground. But that's what you then want to do, sort of see if you remove the right things. Oh, and here again. So you see the difference in, and of course, so we have slight problems along this here because this is also a boundary, but now we don't have anything on the other side because that's the survey boundary, and it's very tight. I mean, of course, maybe that's because it looks to me there was cut off with a shapefile. Because there should be some data otherwise. I don't know the end count procedure of doing that, but it looks like in the end they just get a shapefile and they clip out everything that's not supposed to be delivered. And they were a bit too tight here. There's a rock standing out that's been also cut off. I mean, assuming that here, I would have been a bit more generous here with delivering the data along the edge. I mean, lots of stuff disappears here, obviously, since it's mostly buildings. So you see here, it really only affects the area where you have stuff built. All the stuff where there's nothing built, nothing disappears. And here we do have, yeah. All right, I'm quite happy with the results, I must say. So I didn't really try that before. I went through it with you the way I would do it if I was given that data for the first time. So the last thing I wanted to show you, I think that's pretty much everything I wanted to show you in terms of creating DTMs and DSMs. Remember again, I wasn't creating DTMs and DSMs today. I was creating hill-shaded versions of DTMs and DSMs. The only difference, if you create the actual elevation models, is you check, you go the radio button, actual values. Maybe I do this just once, actual values, and then you create a different kind of output, like the, TIFF or bill. And maybe I'll just do it just for to show you that it just works just as fine. And start. Now I'm outputting bill files, and there's no minus hill shade anywhere. So I'm not outputting hill shades. They are floating points. And now let's load it into a very good GIS processing package, like this one. So here are all the bill files. Bill is it's not a very compact format. It's, well, way more compact than .asc, which is a very slow format. I usually never use it unless I want to debug something and I want to look at the values in a text editor. Drag and drop. Okay. So here I got this, and if you raster. How does this work again? Every time I do it again, oops. Okay. I wanted to merge them into one, but every time I do it, I always have to spend some time reminding myself how to actually do it. So now they're all shaded individually with their own, own shading. And oh yeah, what I wanted to show that, we do. And they're all shaded individually, so that it looks like there's a discontinuity, but there is not. And we have pixels all the way into the corners. If you wanted to, and I don't expect you to follow this now, you can maybe just do that for one tile every 2 meters. Moves a little bit. Last to ISO can compute ISO lines, ISO contour lines. I'm just going to do it for this one. And again, I would keep only the first returns, and then drop classification 7. Run. So with last to ISO, you can create contour lines. I create now a contour line every 2 meters from the, not the DTM, but the DSM. So that's going to be a lot more contour lines than you have. Because I don't have the now I have the shapefile here. And I can drag and drop that in here. And then I have my, oh, and I didn't cut off the buffers. So now I got my contours. But you see, this time I didn't cut off the buffers. So I have them, this is a 25 meters here. I just wanted to show you a little bit of a GIS composition at the end. You know, that you, yeah? No, it was last to ISO. I mean, that's what I just did. I didn't really do that for you to follow because, you know, you did enough today. Last to ISO, you can do contours. 2 meter. These are 2 meter contours of the DSM. So everything is included, but no clouds, you know, otherwise you would see a very funny contour somewhere. But we did remove the clouds. But, you know, it's just a nice for people that like to look at stuff. Contours are not useful for computers. Computers actually don't like contours at all. Contours are only useful for our perceptual vision because we are very good at reading them. Okay, now let's quickly do some full waveform stuff. Just a little glimpse, at least. If you copied, I mean, you don't have to follow this, but if you copied the pulse tools folder, you have sort of a part of, you have that as well. I mean, there were, but that's not something I'll ask you to follow along now. I just very quickly want to give you an idea what full waveform looks like. So pulse waves is that format to store and distribute full waveform data. And this is one of the first data sets to export it by a Regal into the format. And you see points here, but these points are actually not LiDAR points. These points are not even any points that have anything to do with anything on the ground. These points are just used to pick a waveform. The waveform is a green thing. And if you remember before when we showed the pulses, that's sort of one of these pulses in space. And you wonder, why is that pulse, why does it have a hole? Well, that's because the Riegel scanner, when it samples the waveform that comes back, it only samples, or it only stores it, when there's information coming back. So it's like, you know, when you, in the old days, I don't know if you remember the old days of making tapes, you know, I'll listen to the radio and there comes a song I really like, I press record. The song is over, I press stop. And then, you know, an hour later, another good song comes, I press record again. So it only records when there's interesting signal. You know, the commercial break, that's like noise to me. And so that's where the commercial break is. Of course, that's just noise. The scanner didn't register any returning signal. So that's why the waveform, which you see in blue down here, maybe you don't see it. The waveform, which is the blue waveform down here, was recorded in 2 segments, the blue one. 1 segment, 2 segments, and very likely this is the moment it hit the ground. Very strong return. So the moment it hit the ground, where is this guy? Is here. That's a bit hard to see, so let me scale it up a little bit. Scale min to max. There you go. Here, where the red turns, where the green turns red, that's the place I have a return. I would have a return if that was discrete LiDAR. So all these points you see here, they are really irrelevant. These points you see here is just, and you see that point here, it's just the last point of every shot that was stored to file. I shouldn't say point, that's maybe misleading. It's the last sample that was digitized. You start recording, you end recording. And there are like, I don't know how many, 500,000 shots in this file here maybe, or 3 million. So I think I see 3 million points, but these points have nothing to do with the things on the ground. This is just the moment I stop the recording for good. And I can use these now to pick, to pick a new waveform. I want to see the recording of this one. Okay. Here it hit something. And then the recording stopped right here. So these points are only meaning end of recording. It's the last sample that was stored for that shot, for that digitization of that shot. Actually, I also stored the first ones. Oops. So now everybody's hanging. See it? Now it's hanging from this one. This is a noise sample. You start recording when if you're good with making recordings of music tapes, you start like 3 seconds before the song actually starts. Then you get, the beginning of the song, and then you stop just after it ended. And you don't, and that's exactly what we see here. The signal, that's when you actually get signal. So the recording starts before the signal, and then it goes on and nothing really happens, and eventually the recorder turns off the recording. It still keeps on sampling, but it doesn't record anymore to save data. And below again in blue, you see the very strong hit, and that was, I would say that is a straight ground hit, single return. This waveform, if I would make it into a discrete LiDAR, it would be most likely a single return shot. Because if I look at the waveform, this is The timeline, yeah, well, I mean, this is a signal in space. That's the area of space that's where the signal was. That's where it comes from. It's in space, georeferenced. And if I would make a discrete LiDAR sample now, I would get a point here. That would be my LiDAR point. One LiDAR point, it would be yellow. Let me go back to the last return. So now I'll pick one, this one here. Oh, look at this one. This looks to me like a canopy hit where the laser didn't have enough energy to come down to the ground, because clearly the ground is more farther below. And this is a bit of a smeared out, shape. Maybe it becomes clearer if we look at more than one return. So first, let me scale it back down. So the blue one is a plot. The blue one is a plot of the returning signal. It's 80 samples long in this particular case. The red one, you can forget about the red one. The red one is the outgoing shot. Shot at the plane about 3,000 nanoseconds earlier. It is. It's just that was for shot. It should be a Gaussian in the ideal case. But the shot energy varies from shot to shot. So apparently we had one hit here, and then one hit followed by a strong hit. So that looks like shrubbery ground. Oh, that's a beautiful one. Look, a very long one, sampled with 2 segments. So it hit something here, then it hit a little bit here. It hit something and then something bigger. And then 80 samples were up. It only records 80 samples at the time, this particular setting of the scanner. And then it said, okay, I guess nothing else is going to come. And then, oh, there's more coming. So it turned the sampling back on, another little bump. And this is probably the ground. Maybe not, I don't know, but probably. So, and the same, this green line, you have to take the blue, you have to take this blue plot, and it fits right on top of that laser shot. You see the little gap is exactly the gap there. And the green to red shading corresponds exactly to the amplitude of the plot. So that's why wherever I have a bump here, I have a slight shading here. Maybe it's easier if I turn off all these points. And I change the shading a little bit. And maybe I go back to min-max. See? That is one shot. And you see wherever the laser hits something, I get a little bit of energy. And now let me show you more than one shot. Like 11 pulses in a row. Still, I only show you one plot. That's the one from the middle. But now you see 11. So there you see. That's 11 shots right next to each other. And I would say, just looking at this clearly is the ground. And this is probably vegetation. Yeah?
So if that strong signal is the ground, why do you have information below the ground? What appears to be below
Where? What do you mean after the ground?
So you said that strong return, that deep red is the return from the ground.
Yeah?
And further down that same line, which would be after in time,
Yes?
you still have some signal there.
Yeah, but I mean, if you record a song with your tape, you press record the song, and you're on the toilet, and now the song ends, and you're like, oh my God, you run, and then you press stop. Now you recorded more. Well, they always record more, a little bit more. How much more depends on what you say. You say always record 80 samples, or always record 120 samples. Then it depends on when you start it. The start is really the one that triggers the recording. You're like, oh, my favorite song. You run and you press start. Now, you don't always record 5 minutes. And here they always record a certain amount of samples after they start. That's like if you would always say, I want all my songs to be 5 minutes, not less, not more. Then sometimes you would go halfway into the next song, except it's just going to be noise. Psh, white noise.
That's why you said it was not really a spatial distribution of the points.
That's why I said the last returns that are there, that's where the recording ends. But they have nothing to do with the LiDAR returns. That's just where the recording ends. If you use a different setting, I use 100 segments instead of 80 segments, then all these points are going to be shifted down by 20 points. Yeah. So let's show a few more pulses. And so that's full waveform. This is full waveform. It's like an X-ray scan. It also comes in green. Or here again. Here you see more properly how it was the segments. These are the segments that are actually written down to file. Up in the air. They want to write as little as possible because the data flows are gigantic.
These are values between 0 and 255?
These are all 8-bit samples. This is a regal scanner. If it needs more than 8 bits, a second sampling is done with a higher dynamic range. It's actually 2 8-bit channels. You can think of it as there's one very sensitive channel that's always looking for the return signal. And then there's another one just like that wearing sunglasses. So in case the low intensity gets blinded because you hit a mirror or a white sheet of paper, and then the return signal distorts, it comes out at the top, then the one with sunglasses will record. And so you have to pick the higher channel whenever it's recording. It's only turned on, or it's only written to file, if the sensitive guy, the sensitive receiver, is blinded. And so this is almost like a volumetric rendering now. It's a pseudo-volumetric rendering, but maybe you can you get a good idea of the forest now when I move it around. So this is full waveform. So that's why when people have points, I don't really call that full waveform processing. This is how full waveform data looks like. And this is how it looks in green. You don't see so much here anymore. The workflow doesn't really exist yet. These are sort of the starts of, I mean, the workflow exists to extract points from that. And also there's a tool in you have that tool too, it's called pulse extract, and it takes that file as input and produces a file with LiDAR returns as output. And slowly it gets another interesting observation. You see that there seems to be a second ground below the ground. That is now because I'm adding, in the volumetric entering, I'm adding up all these on top of each other. I'm drawing all these individual shots. There's a ringing happening. You see that ringing also here. If I get a strong return like this one, shortly after the return, I get a little bump. It's also visible in the outgoing shot. I get these little bumps. This is called a sensor ringing. It's a physical problem with recording the signal. And it gives you a small bump after every very strong hit. You see clearly this second layer. When you do the extraction of points, you must be careful not to extract these guys, because they are systematic, sort of like an echoing, you know, shortly after the.
In this case, you filter with something like Fourier transform or something?
I don't do anything. I just display the data as it comes. This is not processed. This is a raw data like it's recorded.
But in this case, it's possible to apply double Fourier transform? Because you have some kind of cycles.
I haven't done much processing of this data yet. The only processing I did so far is decomposition. You see, now I'm finding the peaks. And this is basically how you get the returns. And I find here 1, 2, 3, and there's a small one, 4, 5, 6. 6 returns. I would give you 6 points for this particular shot. Which one is that? And some shot somewhere in the middle of all these many shots. This is how Regal does it. They always record the full waveform, and in post-processing, they get the returns. So they are not limited. There can be unlimited return. I mean, of course, maybe 12, 13, 14 is the reasonable maximum. And here I just get 2. I get this one somewhere up high in the canopy, and then I get a very strong ground hit. And you say, oh, why did you record all this? Well, that's because the scanner was set to always record 80 segments once it starts recording. And here you see the ringing very clearly. Strong hit, and afterwards a little bump. And these many bumps together give you that very clearly visible second layer, which needs to be taken care of if you do a waveform decomposition, it's called, when you try to fit Gaussians, because you shoot a Gaussian, and if you hit a flat surface, and that's what you sort of expect, you should get back a Gaussian, and then you try to find the outgoing shot, which is the red one. You're looking for small versions of that in the returning waveform. And of course, if you have slanted surfaces or if you have vegetation, these get smeared out. Maybe we see some interesting ones. So that would be 3 discrete returns. Here you see a typical, like a smeared out thing. This is like in the canopy. I hit the canopy and then I hit it a bit more. Now, should that be 3 returns? Well, that's what this algorithm will give you. My algorithm, or rather the algorithm that somebody gave me and that I adopted and put in here. Other people use a different algorithm, you get a different number of returns. That's what I meant with a black box. But I have the waveform. I can use, it's not a black box because the algorithm I wrote, and I can switch it out against another algorithm that I may like better. Yeah, 4 returns I would get with this particular algorithm. These peaks are where my LiDAR points are. First, this will be my first return, last return, intermediate ones. And the last sample is here. That's the points I showed earlier, but they are meaningless. They mean nothing. It's just like where the noise is. But that's where the recording ends. So,
what happened with the airborne coastal surveys when the pulse hit the ocean and penetrates to the ocean floor? It's appearing can see something in the waveform?
well, well, an interesting waveform I looked at was when you hit a cloud. And you have this Gaussian return when you hit like a hard ground. If you hit a cloud, like a foggy cloud, you get something like that looks like this. Up, but not very strong up, like up a little bit, and then you scatter back energy until the energy is gone. That's how a foggy cloud kind of return looks like. Now, waveform analysis is super important when you do what's called bathymetric LiDAR. You use a different wavelengths for the LiDAR, a green LiDAR instead of an infrared LiDAR, because it can actually penetrate the water. And as in the moment it penetrates the water, everything changes. It travels with a different speed. It refracts. So, if it hits straight on the water surface, it pretty much goes straight. But if there's a wave in the water at that place, or if it hits like this, we learned that all in, in high school physics. Like medium that's not so dense, and the medium more dense, it reflects this direction and the other way. You have to account for this in order to get the return at the right location. So yes, you can see everything in the waveform, and the analysis of the waveform that's probably the field that does the most waveform analysis right now, is bathymetric LiDAR, because they really have to find the water surface in the waveform, and then from that moment on, everything is a little different. Yeah.
You can, or maybe you don't know, but you can regulate the energy of the pulse?
Different scanners do it differently. The Leica uses something, it's called the gain control. They basically, when they start hitting surfaces that don't reflect so well, they increase the energy. And then they also store that to the file, how much energy they just shot. I'm not so sure how this does it, but they don't give you the waveform. They have no way of giving you the waveform. There's a hardware that is analog, and then you can get the waveform, but it's a separate hardware. They have nothing to do with each other. In the Regal scanner, you always record the waveform, and then you get the returns in the post-processing. I am right now not entirely sure if Regal has a mechanism so that you fire with the higher energy if you get less returns. So I know Leica does it. It's called gain control. I'm not sure Regal does it, and I'm also not sure what Optic does. But of course, you can't fire with arbitrary high energy just to get a low surface, because there is this eye-safe requirement that you should not fire with more energy so that the person looking with binoculars at your plane shouldn't go blind. That's that's sort of the very.
What's the maximum power?
I don't know. That's, I'm not really in the survey side that deep, but it's usually done with flying height. They use a certain power setting and then say, well, this power setting you have to fly at least this high above ground in order to be eye safe. Because of course, if you fly farther away, the energy spreads more and it becomes more safe. But if you fly low, then you can't use the highest power setting and so on.
So 6 returns means see objects between the ground and source?
6 returns means you hit 6 different things, or maybe one different things with 6 branches. Like, it could be one tree, you hit 6 branches and then you were out of energy and you still haven't hit the ground. It's in tropical rainforests. So there's also I have a whole bunch of pictures up where you can look at waveforms from a tropical rainforest, and very often the laser gets stuck in the canopy and never reaches the ground. Or in a cloud, if you have clouds often hang above tropical rainforest, you shoot into the cloud, it makes a It's very easy to see what the cloud returns, just looking at the waveform, because they look completely different, the shape of the waveform than a hit of anything.
So you can figure out more or less the vertical distance between 2 peaks.
Yeah, and the beautiful thing is, if all that you're interested in is relative heights, meaning the distance between the last, between 2 things, your accuracy is super high, because within the system, it's incredibly high accuracy.
You calibrate that.
To know where you are in the world, that is the hard part, because then you have to rely on the GPS signal, on the plane's flight, and so on. But within one LiDAR scan, especially within one shot, if you hit the edge of the house and then you hit the ground, you have a super high precision, measurement from the edge of that house to the ground, because the relative accuracy is very, very high.
Still, your ground can be on a slope, right? It doesn't have to be horizontal.
Yeah, so you only know.
How often you go down and see exactly what you figure out?
Well, I never, except that one time when I went into the forest and, got all scratched up and bloody and it was interesting, but so I don't do surveys very often myself. I would like to do it more often, because it's kind of, you get a better feel for all the problems involved. But small surveys are fun. Big surveys are boring. They fly back and forth and back and forth.
There's one kind of question. From what we read, how this applies to science and society, how does this apply in war?
Well, I don't know. In the Philippines, there is an area where they have rebel activity, because people are not happy about being part of the Philippines, because Philippines is a very Christian country, and the people in the South and islands are traditionally have been Muslim, and they're kind of, forced, or they're supposed to be in the Philippines, but they don't want to be. They want to be their own country. So I was telling the guys, you want to fly LiDAR there? I wouldn't fly LiDAR there. If I was a pilot, I would refuse to fly, because if I was a rebel and I would see a survey plane flying LiDAR, and I would know what LiDAR can do, it can find anything that's below the forest. And usually the only way a weaker kind of freedom fighter, you can call it rebels also, can win against an oppressive power like ESRI, is with guerrilla tactics, and you have to hide and then come out and hide again. So if they fly over, the area and they find where you're hiding, you toast. So if I would be a guerrilla, like one that uses violence and fights armies, I would shoot down that plane for my own survival. So I think LiDAR is very powerful in seeing below trees what's hiding there. That's one obvious, one obvious use of LiDAR. And of course, the Army Corps was flying all of Afghanistan and Iraq, to make detailed maps, and I don't know what they're doing. So LiDAR is not really real time. So it takes a bunch of months. It's not like you can fly a LiDAR and make tactical decisions right away. But people want to get detailed maps so they know how to move, move supplies, and so that's why LiDAR, I guess, that's why they flew LiDAR in Afghanistan and Iraq, is to make maps for future missions. Yeah, I'm usually more with the rebels, so I give lots of LiDAR workshops to rebels, just to equal the playing field. Okay, 10 to 6. I'm around. Tomorrow they're going to be in another awesome workshop on something I'm super interested in hearing about with Cloud Compare. But I'm still here, so if you think of some other questions, hit me up, or tonight, at least after I had a few beers, maybe, the icebreaker. Okay, if there's no more questions, there's one more tiny question. Yeah, you do it in the viewer, and if you, I'm not online anymore, but you do have, as part of your distribution, you have this really cool little PDF called Laszlo's Tutorial 4, Manual LiDAR Editing with LastView. And it goes in great detail through every little step of how to do it, So, yeah, there you go. It's going to go like this, and then the points are gone. All right. I hope it's tiny.
So are there any plans to make various tools for other platforms, Linux?
It works really great through WinE, through Wine. So many people use Laszlo through Wine and other platforms. Of course, the GUIs don't work so well, but most people that work on Linux and Mac OS, they're quite capable of working with the command line. You check the same scripts, you just put WinE in front of every command, that's it. The performance is 20 to 30% less good, but hey, Lassos is still faster than most other LiDAR processing software out there. So even with the minus 20%, you're probably still faster than, than other. Yeah. The open source tools, last to last, last info, last merge, text to last, you can just compile them on Mac OS yourself. I get occasional requests for native Linux versions, but unless somebody gives me a big chunk of money, I'm not going to do that. Porting work is really boring. And I have so many interesting things to work on that I'd rather work on the interesting things. And it does work through WinE. So, oh, don't forget the chocolates.